For nearly 40 years, the electric utility industry has been using fire-resistant fluids in their turbine hydraulic fluid systems. These fire-resistant fluids, also referred to as FRFs, are required not only to reduce the possibility of a catastrophic fire resulting from a system leak, but insurance companies demand the use of FRFs on turbine hydraulic fluid systems. The predominant FRF that has been used in these systems is a phosphate ester fluid. These phosphate ester fluids have superior fire-resistant properties and have performed well over the past 40 years. Unfortunately, the phosphate ester fluids are now being blamed for numerous problems experienced in hydraulic fluid systems. Extensive testing conducted over the past few years by numerous independent laboratories have yielded the same conclusions. The major contamination being observed in hydraulic fluid systems is being generated by the FRFs. In order to understand why this is occurring, it is important to understand some of the characteristics of the FRFs. First, the phosphate ester fluids naturally create aggressive acids, such as phosphoric acids. If these acids are left unchecked, severe corrosion of the system components could occur, resulting in a forced outage on the unit. In order to control the development of the acids, acid control filters were added to the hydraulic power units. Initially, Fuller's earth filters were used to control the FRF acidity. These filters are still in wide use throughout the industry. During normal use, Fuller's earth filters continuously release small quantities of magnesium and calcium in the form of metal salts into the fluid. As the fluid's acid levels increase, these metal salts continue to be released in greater quantities. Metal salts in sufficient quantity ultimately cause a chemical reaction to occur in the fluid, which results in the formation of gels. Gels are simply FRF in a gel form with metal salts present. These gels are capable of passing through the smallest of filter media as long as there is sufficient flow through the filter. Once the gels are picked up by the hydraulic pumps, they are circulated throughout the entire hydraulic fluid system. Over a period of time, the gels form as hard deposits called varnish on the tubes and pipes of the hydraulic fluid system. The varnish does not generally form on the components of the system since they move and can ultimately scrape off the varnish buildup. On the other hand, the pipes have no moving parts. The fluid flowing through the pipes is under high pressure, but the flow is laminar and there is very little turbulence. This combination allows for easy varnish formation. The majority of the pipes in the system are located downstream of the main pump discharge filters. Over time, the varnish formed on these pipes can break off and enter the system entrained in the fluid. This condition can occur as a result of excessive varnish buildup, high vibration or shaking of the pipes during system upset, such as a turbine trip, or in some cases, simply a result of a normal valve test. The varnish is very hard, and since the varnish is deposited downstream of the pump discharge filters, it can cause the most amount of damage to the system components, such as the servo valves, solenoid valves, and hydraulic actuators. In order to eliminate the release of metal salts and ultimately the formation of gels and varnish, select sorb filters were introduced about 20 years ago. Experience with select sorb filters indicate they have a tendency to release ultrafine particulates into the hydraulic fluid system that cannot be removed with standard filtration. Over time, these ultrafine particulates can cause silting to occur in mechanical components that are not routinely tested, resulting in a failed test due to a sticking valve. Recently, ion exchange filters have been used in place of Fuller's earth and select sorb filters to control the acids in FRF. Ion exchange filters do not release any metal salts, therefore do not cause any gel or varnish formation. However, ion exchange filters can compromise or reduce the resistivity or resistance to conduct electricity of an FRF fluid. Low resistivity can cause etching of the servo valves. The etching of the servo valve spools will cause increased flows through the servo valves. As these flows increase, the hydraulic fluid pumps work harder and can ultimately experience premature wear of their internals, causing pump problems. In some servo valves, the etching can cause problems with the torque motor nozzles, causing the servo valve to respond erratically or in some cases fail to the closed position and remain there. The cause of low resistivity in FRF has been directly related to high acidity, high conductive water content, and high ferrous particulates in the fluid. Even though the ion exchange filters do not cause resistivity to drop below OEM recommendations, they leave lower margin for error with acids, water, and particulates. No system is immune to problems. However, careful evaluation can identify a problem before it occurs. In order to determine whether a problem exists and to what extent the problem is affecting the system, fluid samples, filter analysis, and visual inspection of the components should be done on a regular basis.